So we're going to talk about hydrogen bonds, and a hydrogen bond is a specific type of dipole-dipole interaction. So it's not really its own thing, it's just a more specific version of what we were already talking about. A hydrogen bond is quite strong, all dipole-dipoles are, and it's the result of a polar covalent bond. A hydrogen bond occurs when a hydrogen atom is covalently bonded to a highly electronegative element. And remember that periodic trend. If this is what the periodic table looks like, electronegativity increases from left to right, and it increases as we go up. And so the most electronegative elements tend to be in this area here, the nonmetals, excluding the noble gases. So these are elements like fluorine, oxygen, and chlorine. So what happens, this highly electronegative element is pulling on the electrons, not sharing very well, and it's causing hydrogen to have a partial positive that interacts with the partial negative of the next molecule. So let's look at something like this. This is an ammonia molecule, and it has three hydrogens kind of on one end, and this is in 3 dimensions here. So 3 hydrogens, and they're bonded to a nitrogen. Now nitrogen is in the top right. It's not the most electronegative, but it's fairly electronegative. And so we end up with nitrogen pulling all the electrons towards itself, and we have this partially negative region, leaving down here to be partially positive. So let's say this ammonia is dissolved in some water. So here's a water molecule. Actually, I'll make it blue. So here's a water molecule, and here's another water molecule. Water is also a polar molecule. It's hydrogen covalently bonded to an extremely electronegative element, which means that this oxygen side is going to be partially negative, leaving the hydrogen end to be partially positive. It just is a matter of the electrons are being pulled towards the oxygen and away from the hydrogens. And so we can draw dotted lines to represent these hydrogen bonds. So a hydrogen bond will be between a partially positive hydrogen of one atom and a partially negative or a highly electronegative element of the next molecule. So there would be a hydrogen bond here. And that wouldn't be the only one. There would be a hydrogen bond between this hydrogen and this oxygen. And there would be another possibility here, this oxygen of the water and this hydrogen. And they are interacting, and they are working to pull all of these molecules closer together. Hydrogen bonds are also responsible for some of the odd behaviors of water. Water is unusual for a few different reasons in the chemical world. For one thing, It's unusual because its volume is greater as a solid than a liquid. In general, as things have a lower temperature, they tend to get smaller. So liquids, as they turn into a solid, will become slightly smaller in volume. But it's not the case with water. Once water freezes, its volume increases by about 10%. It's a significant amount. That's why when you put something in the freezer, like a can of Coke, and you leave it there too long, the water expands and the can can burst. So most substances don't do this. They continue to become smaller as temperature decreases. The volume of the ice is larger because of the hydrogen bonds. These hydrogen bonds cause the water molecules to create a more orderly arrangement as it freezes. When water begins to freeze, these hydrogen bonds will turn the molecules so that they are lined up positive to negative, positive to negative. So it might look something like this. So I'm going to leave off the electrons of the hydrogen, the oxygens here, because I'm going to draw a bunch of them. So I'm going to say, here's a water, and this one is starting to freeze. Here's a water. Here's a water. Here's a water. And in one sample of water, like let's say a glass of water, if it's freezing, would have very, very large amounts of these water molecules. Things like a number times 10 to the 23rd times 10 to the 25th in terms of how big this number is. And so they're lining up, and their hydrogen bonds are causing these molecules to turn. And let's, for 1 second, say that there was another water over here that, let's say it's here. And as a liquid, it was more like this. But it doesn't really want to freeze like that because these positives are kind of close together. And so they start pushing and these start pulling, and it ends up turning this molecule so that they're nice and lined up. And it's all of this rearranging that causes the water to expand. It's the same idea that's responsible for the surface tension of water. Now, a lot of you, by the time you get to my class, you've gone through this lab in 8th grade where here you have a penny that is on the lab table, and you have an eyedropper with water, and sometimes there's other substances to compare. But so you start taking this eyedropper and you put a drop here, and it's right there. And you put more drops, and eventually you start to get this puddle on top of the penny. And as you start adding even more, you would expect it just to fall over the side like a waterfall. But in reality, what you see is the water just starts to stand up higher. Something like that. And this is that idea of surface tension. Let's label this so we know what we're talking about later. That's the water. That's a penny, and that's the surface tension. So here is another example, and this one has to do with some hydrogen bonds. And so I'm going to use a couple of different atoms. I'm going to say that black is carbon, the black ring with the white on the inside is hydrogen, and the red one, which is a little bit bigger, is oxygen. Now, if you don't have colored pencils or crayons with you, it's fine. Don't run out and grab them. But just try to keep in mind which one is which. So let's draw a molecule here first. And so here's an oxygen, here's a hydrogen, here's a carbon, and this carbon has 3 hydrogens on it. This is what we would name CH3OH. That's not really important at this point. So we dissolve it in water. So we're going to put a couple of waters around. So I'll do the red first. I'll come back for the hydrogens. And this is not too much different than something that students have been asked on the AP chemistry exam in recent years. So you'll see a picture like this, and it'll say, draw a line to represent a hydrogen bond. And this question is actually fairly simple. You want to draw a line to represent a hydrogen bond. And interestingly, with AP, you only have to draw one. There's a potential for quite a few hydrogen bonds in this picture, but you only have to draw one. And it's going to be between a hydrogen and a highly electronegative atom. So it could be from here to here. There's a hydrogen and a highly electronegative atom. Let's make these dotted. It could be between this oxygen and this hydrogen. It could be between this oxygen and this hydrogen. Let's just leave it with the 2 that I have. And so this is something they've been asking. A similar idea over here. So let's draw another couple of molecules. Here is this. This molecule has a common name. It is rubbing alcohol. And rubbing alcohol is pretty easily dissolved in water. In fact, the rubbing alcohol you buy in stores comes in different concentrations, which is referring to how much of it is the alcohol and how much of it is the water. So I've got a few different waters here. And so let's draw a dotted line to represent a hydrogen bond. And it's a hydrogen that is interacting with a different molecule, an atom that is highly electronegative. So it could be, let's say, this hydrogen with this oxygen. Or it could be this hydrogen with this oxygen. Those are both places where we would see hydrogen bonds that occur. Now, take a look down here. These are carbons and hydrogens together, and I'm not drawing any hydrogen bonds on this side because carbon has hydrogens bonded to it, but carbon is not very electronegative. The difference in electronegativity between carbon and hydrogen is 0.4, which makes it nonpolar, which means that these are not going to form hydrogen bonds with respect to these waters. The only part of this alcohol molecule that is really soluble in water is this part, and that is what you call the alcohol alcohol group. Again, that's more of organic chemistry than chemistry 1. But these are the hydrogen bonds, and that is something you can expect to see over the next couple of weeks or couple of years through your high school and college chemistry careers.